little step here, that's what's going on. We have some encoders, we have some decoders, we do a transformation to summarize, we have a softmax to get probabilities, and then we generate based on those probabilities. Cool. Next up, in the encoder, in each of these encoders, this is what it's going to look like. So we have multi-head attention, which I'm going to delve into a second here. So after this multi-head attention, we have a residual connection. So in case you aren't familiar with residual connections, I might have went over this before, but pretty much what they do is it's a little connector. So I don't know, let's say you get some inputs X, you have some inputs X down here, and you put them into some sort of function here, some sort of like feed forward network, whatever it is. A feed forward network is essentially just a linear, a ReLU, and then a linear. That's all feed forward network is right here. Linear, ReLU, linear. And all you do is you wrap those inputs around, so you don't actually put them into that feed forward network. You actually wrap them around, and then you can add them to the output. So you had some X values here go through the ReLU, and then you had some wrap around, and then right here you simply add them together and you normalize them using something called layer norm, which we're going to cover in a little bit. And what the reason why residual connections are so useful in transformers is because when you have a really deep neural network, a lot of the information is actually forgotten in the first steps. So if you have, your first few encoder layers and your first few decoder layers, a lot of the information here is going to be forgotten because it's not being carried through. The first steps of it aren't explicitly being carried through and, sort of skipped through the functions. And yeah, you can sort of see how they would just be forgotten. So residual connections are sort of just a cheat for getting around that, for not having deep neural networks forget things from the beginning and having them all sort of work together to the same degree. So residual connections are great that way. And then, at the end there, you would add them together and then normalize. And there's two different ways that you can do this add a norm. There's add a norm and then norm and add. So these are two different separate architectures that you can do in transformers. And both of these are sort of like meta architectures. But pretty much pre-norm is the normalize then add, and then post-norm is add then normalize. So in this attention is all you need paper proposed by a bunch of research scientists was initially you want to add these together and then normalize them. So that is what we call the post-norm architecture. And then pre-norm is just flip them around. So I've actually done some testing with pre-norm and post-norm, and the original transformer paper turned out to be quite actually a lot better, at least for training very small language models. If you're training bigger ones, it might be different, but essentially we're just going to go by the rules that we use in here. So add a norm. We're not going to do norm and add. We're doing add a norm in this video specifically because it works better, and we just don't want to break any of the rules and go outside of it, because then that starts to get confusing. And actually, if you watch the Andrej Karpathy lecture on building GPTs from scratch, he actually implemented it in the pre-norm way, so normalize then add. So yeah, based on my experience, what I've done on my computer here is the post-norm architecture works quite better. So that's why we're going to use it. We're going to do add, then normalize. So then we essentially feed this into a feed-forward network, which we covered earlier. And then how did it go? We have so our encoder. We do a residual connection from here to here, and then another residual connection from like outside of our feed-forward network. So each time we're doing some other things, like some computation blocks in here, we're going to have a res connection. Same with our feed-forward res connection. And then of course, the output from here would just, when it exits, it's going to feed into the next encoder block if it's not the last encoder. So this one is going to do all this. It's going to feed into that one. It's going to do the same thing, feed into this one, going to feed into that one. And then the output of this is going to feed into each of these decoders. All the same information. And yeah, so that's a little bit scoped in as to what these encoders look like. So now that you know what the encoder looks like, what the feed forward looks like, we're going to go into multi-head attention, sort of the premise, sort of the highlight of the transformer architecture and why it's so important. So multi-head attention, we call it multi-head attention because there are a bunch of these different heads learning different semantic info from a unique perspective. So let's say you have 10 different people looking at the same book. If you have 10 different people, let's say they're all reading the same Harry Potter book, okay? These different people, they might have, different cognitive abilities. They might have different IQs. They might have been raised in different ways, so they might interpret things differently. They might look at little things in that book, and their mind will, or they'll imagine, different scenarios, different environments from the book. And essentially, why this is so valuable is because we don't just want to have one person, just one perspective on this. We want to have a bunch of different heads in parallel looking at this same piece of data, because they're all going to capture different things about it. And keep in mind, each of these heads in parallel, these different perspectives, they have different learnable parameters. So they're not all the same one looking at this piece of data. They're actually, they all have different learnable parameters. So you have a bunch of these at the same time learning different things, and that's why it's so powerful. So this scaled dot product attention runs in parallel, which means we can scale that to the GPU, which is very useful. It's good to touch on that. Anything with the GPU that you can accelerate is just an automatic win, because parallelism is great in machine learning. Why not have parallelism, right? If it's just going to be running the CPU, what's the point? That's why we love GPUs. Anyways, yeah. So you're gonna have these things that are called keys, queries, and values. I'll touch on those in a second here, because keys, queries, and values sort of point to self-attention, which is literally the entire point of the transformer. Transformer wouldn't really mean anything without self-attention. So I'll touch on those in a second here, and we'll actually delve deeper once we hit this sort of block. But yeah, you have these keys, queries, and values. They go into scaled dot product attention, so a bunch of these running in parallel, and then you concatenate the results from all these different heads running in parallel. You have all these different people. You concatenate all of them, you generalize it, and then you apply a transformation to a linear transformation to pretty much summarize that, and then do your add a norm, then feed forward network. So that's what's going on in multi-head attention. You're just doing a bunch of self-attentions in parallel, concatenating, and then continuing on with this part. So scaled dot product attention, what is that? So let's just start from the ground up here. So we'll just go from left to right. So you have your keys, queries, and values. What do your keys do? Well, a key is, let's just say you have a token in a sentence, okay? So if you have, let me just scroll down here to a good example. So self-attention uses keys, queries, and values. Self-attention helps identify which of these tokens in a sentence, in any given sentence, are more important, and how much attention you should pay to each of those characters or words, whatever you're using. We'll just use words to make it easier to understand for the purpose of this video. But essentially, imagine you have these two sentences here. So you have, let me bring out my little piece of text. So you have, oh, that didn't work. So imagine you have server, can I have the check? And then you have and you have looks like I crashed the server. So, I mean, both of these have the word server in them, but they mean different things. Server meaning like the waiter or the waitress or whoever is billing you at the end of your restaurant visit. And then looks like I crashed the server is like, oh, there's actually a server running in the cloud, not like a person that's billing me, but an actual server that's maybe running a video game. And these are two different things. So what attention can do is it can actually identify which words should get attention here. So it can say, server, can I have the check? Can I have? So maybe you're looking for something, you're looking for the check. And then server is like, oh, well, in this particular sequence, or in the sentiment of this sentence here, server is specifically tied to this one meaning, maybe a human, someone at a restaurant. And then crash the server. Crash is going to get a very high attention score because you don't normally crash a server at a restaurant. That doesn't particularly make sense. So when you have different words like this, what self-attention will do is it will learn which words in the sentence are actually more important and which words should it pay more attention to. So that's really all that's going on here. And K, the key, is essentially going to emit a different, it's going to emit a little tensor for each of these words here saying, what do I contain? And then query is going to say, what am I looking for? So what's going to happen is if these, like, let's say server, it's going to look for things like, check or crashed. So if it sees crashed, then that means the key and the query are going to multiply and it's going to get a very high attention score. But if you had something like the and the, it's like, oh, does literally in like almost any sentence, so that doesn't mean much. We're not going to pay attention to those words. So that's going to get a very low attention score. And all attention is you're just dot producting these vectors together. So you get a key and a query, you dot product them. We already went over dot products in this course before. And then all you do here, and this is a little bit of a confusing part, is you scale it by 1 over the square root of the length of a row in the keys or queries matrix, otherwise known as DK. So let's say we have our key and our query. These are all going to be the same length, by the way. Let's say our keys is maybe our keys is going to be like 10 characters long. Our keys are going to be 10 characters long as well. So it's going to do 1 over the square root of 10, if that makes sense. And so that's just essentially a way of preventing these dot products from exploding, right? We want to scale them because as we have as the length of it increases, so will the ending dot product because there's more of these to multiply. So we pretty much just want to scale it by using an inverse square root. And that'll just help us with scaling, make sure nothing explodes in unnecessary ways. And then the next little important part is using torch.trill, which I imagine we went over in our examples here. Trill. Yeah. So you can see that it's a diagonal, it's a left triangular matrix of ones. And these aren't going to be ones in our self-attention here, in our torch.trill or masking. What this is going to be is the scores at each time step, the combination of scores at each time step. So if we've only gone, if we're only looking at the first time step, we should not have access to the rest of things, or else that would be cheating. We shouldn't be allowed to look ahead because we haven't actually produced these yet. We need to produce these before we can put them into perspective and, put a weight on them. So we're going to set all these to 0, and then we go to the next time step. Okay, so now we've just generated this 1. we haven't generated these yet, so we can't look at them. And then as we go more and more, as the time step increases, we know more and more context about all of these tokens. So that's all that's doing. Mask attention is pretty much just saying we don't want to look into the future. We want to only guess with what we currently know in our current time step and everything before it. You can't jump into the future. You can only look at what happened in the past and do stuff based on that, right? Same thing applies to life. You can't really skip to the future and say, hey, if you do this, you're going to be a billionaire. No, that would be cheating. You're not allowed to do that. You can only look at the mistakes you made and say, how can I become a billionaire based on all these other mistakes that I made? How can I become as close to perfect as possible? Which no one can ever be perfect, but that's my little analogy for the day. So that's mass attention, pretty much just not letting us skip time steps. So that's fun. Let's continue. Two more little things I want to touch on before I jump forward here. So these keys, queries, and values, each of these are learned through a linear transformation. Just an nn.linear is applied, and that's how we get our keys, queries, and values. So that's just a little touching there if you're wondering how do we get those. It's just an nn.linear transformation. And then as for our masking, we don't actually apply this all the time. You might have seen right here, we have multi-head attention, and then masked multi-head attention. So this masked attention isn't used all the time. It's only used actually 1 out of the 3 attentions we have per layer. So I'll give you a little bit more information about that as we progress more and more into the architecture and as we learn more about it. I'm not going to dive into that quite yet though. So let's just continue on with what's going on. So we have a softmax. And why is softmax important? Well, I actually mentioned earlier, softmax is not commonly used as a normalization method, but here we're actually using softmax to normalize. So when you have all of these, attention scores, essentially what the softmax is doing is it's going to exponentiate and normalize all of these. So all of the attention scores that have scored high, like maybe 50 to 90% or whatever it is, those are going to take a massive effect in that entire attention, I guess, tensor, if you want to call it that. And that's important. Well, it might not seem important, but it's essentially just giving the model more confidence as to which tokens matter more. So, for example, if we just did a normalization, we would have words like server and crash and then server and check. And then you would just know, a decent amount about those. Those would be pay attention to a decent amount because they multiply together quite well. But if you softmax those, then it's like those are almost the only characters that matter. So it's looking at the context of those two, and then we're sort of filling in, like we're learning about the rest of the sentence based on just the sentiment of those attention scores, because they're so high priority, because they multiply together to such a high degree. We want to emphasize them and then basically let the model learn more about which words matter more together. So that's pretty much just what the softmax does. It increases our confidence in attention. And then a matrix multiply, well, we go back to our V here, and this is a value. So essentially what this is just a linear transformation, and we apply this on our inputs, and it's just going to have some value about, what exactly those tokens are. And after we've gotten all of our attention, our softmax, everything done, it's just going to multiply the original values by everything we've gotten so far, just so that we don't have any information that's really lost, or we don't have anything scrambled, just so that we have like a general idea of, okay, these are actually all the tokens we have, and then these are which ones we found interesting, the attention scores. So yeah, we have an output, which is a blend of input vector values and attention placed on each token. And that's pretty much what's happening in scaled dot product attention in parallel. So we have a bunch of these that are just happening at the same time many of these happening at the same time. And yeah, so that's what attention is. That's what feed-forward networks are. That's what residual connections are. And yeah, and then so after this, after we've fed these into our decoders, we get an output. We apply a linear transformation to summarize, softmax probabilities, and then we generate based on that, based on everything that we learned. And actually, what I didn't quite write a lot about was the decoder. So what I'm actually going to talk about next is something I didn't fill in yet, which is why the heck do we use mass attention here, but not in these places? So why the heck do we have multi-head attention here, multi-head attention here, but mass attention here? So why is this? Well, the purpose of the encoder is to pretty much learn the present, past, and future, and put that into a vector representation for the decoder. That's what the encoder does. So it's okay if we look into the future and understand tokens that way, because we're technically not cheating. We're just learning the different attention scores. And yeah, we're just using that to help us predict based on what the sentence looks like, but not explicitly giving it away, just giving it an idea of what to look for type of thing. And then we use mass attention here because, well, we don't want to look ahead. We just want to look at the present and the past, and later on, so see, we're not given anything explicit here. We're not given anything yet. So we want to make some raw guesses. They're not going to be very good guesses at first, but we want to make some raw guesses, and then later on we can feed the added and normalized guesses into this next multi-head attention, which isn't masked, and then we can use this max multi-head attention with the vector representation given by the encoder, and then we can sort of do more useful things with that rather than just being forced to guess raw attention scores and then being judged from that. We can sort of introduce more and more elements in this decoder block to help us learn more meaningful things. So we start off with taking this mass multi-head attention and then combining that with our then afterwards we do a multi-head attention with the vector representation from the encoder, and then we can make decisions on that. So that's kind of why that works this way. If you don't think I explain it like amazingly well, you can totally just ask GPT-4 about it or GPT 3.5 and get a pretty decent answer. But that's how that works. And yeah, another thing I kind of wanted to point out here is these linear transformations that you see. There's a lot of them in the scaled dot product attention. So you have your linears for your value or key value and key query and values. So these linears, as well as the one up here, linears are great for just expanding or shrinking a bunch of important info into something easier to work with. So if you have a large vector containing a bunch of info learned from this scaled dot product attention, you can sort of just compress that into something more manageable through a linear transformation. And that's essentially what's just happening here for the softmax, as well as in our scaled dot product attention here for these linear transformations from our inputs to keys, queries, and values. That's all that's happening. Yeah, if you want to read more about linear transformations, the importance of them, you can totally go out of your way to do that, but that's just sort of a brief summary as to why they're important, just shrinking or expanding vectors. So that's sort of a brief overview on how transformers work. However, in this course, we will not be building the transformer architecture. We'll be building something called a GPT, which you're probably familiar with, and GPT stands for Generatively Pre-trained Transformer, or Generative Pre-trained Transformer, one of the two. And pretty much what this is, it's pretty close to the transformer, this architecture here, except it only adopts the decoder blocks, and it takes away this multi-head attention here. So all we're doing is we're removing the encoder, as well as what the encoder plugs into, So all we have left is just some inputs, our max multi-head attention, our post norm architecture, and then right after this, we're not going to a non-mass multi-head attention, but rather to a feed-forward network and then a post norm. So that's all it is. It's just 1, 2, 3, 4. That's all it's going to look like. That's all the blocks are going to be. It is still important to understand the transformer architecture itself because you might need that in the future, and it is sort of a good practice in language modeling to have a grasp on and to understand, why we use mass multi-head attention in the decoder and why we don't use it in the encoder and stuff like that. So anyways, we're going to go ahead and build this. If you need to look back, if something wasn't quite clear, definitely skip back a few seconds or a few minutes through the video and just make sure you clarify everything up to this point. But yeah, I'm going to go over some more math on the side here and just some other little widgets we're going to need for building the decoder GPT architecture. So let's go ahead and do that. Before we actually jump into building the transformer, or rather building the GPT from scratch, what I want to do is linger on self-attention for a little bit, or rather just the attention mechanism and the matrix multiplication behind it and why it works. So I'm going to use whiteboard to illustrate this. So we're going to go ahead and draw out we'll just use maybe a 4 token sequence here of words. My dog has fleas. Okay, so we're going to highlight which words are probably going to end up correlating together, or the attention mechanism is going to multiply them together to a high amount based on what it learns about those tokens. This is what this is. So I'm going to help us illustrate that and what the GPT is going to see sort of from the inside, what it looks like from the inside. So I'm going to go ahead and draw this out here. So just make a table here. We'll give it 4 of these. And then draw a little line through the middle. My drawing might not be perfect, but it's definitely better than on paper. So cool. We have this. We have my, let me go here, dog has fleas, and then my dog, let's delete that. My dog has fleas. Cool. So, to what degree are these going to interact? Well, it doesn't really give away that much. It's only just the start, so maybe will interact to a low amount. And then you have my and dog. These might interact to a medium amount because it's like your dog. So we might go medium like that. And then my and has, well, that doesn't give away too much, so maybe that'll be low. And then my and fleas, it's like, oh, that doesn't really mean much. My fleas, that doesn't really make sense. Maybe we'll have it interact to a low amount. And then these would be the same thing. So my and dog, so would be medium. And then has would be low. And then my and fleas would also be low. And then you have dog and dog. So these might interact to a low amount. They're the same word, so we'll just forget about that. And then we have dog has. So these might interact to a medium amount. Dog has, so the dog has something. And then dog and fleas. These might interact to a high amount because they're associating the dog with something else, meaning fleas. And we have has and dog. These would interact to the same amount, so medium. And then has and has be probably to a low amount, and then we could do low, or we could do high for this one as well, fleas and dog. So these will interact to a high amount. And then we have has and fleas, so these could interact to maybe a medium amount. medium, and then please and please, which would be low. So what you get, I'll just highlight this in green here. So you get all the medium and high attention scores. You'd have your medium here, high, medium, high, medium, and medium. So you can see these are sort of symmetrical, and this is what the attention map will look like. Of course, there's going to be some scaling going on here based on the amount of actual attention's heads we have running in parallel, but that's besides the point. Really what's going on here is the network is going to learn how to place the right attention scores, because attention is simply being used to generate tokens. That's how the GPT works. It's using attention to generate tokens, so we can make those sort of attention scores, how they're placed, we can make those learnable through all of the embeddings, everything we have in the entire network can make sure that we place effective attention scores and to make sure that they're measured properly. So obviously I didn't quantify these very well, not with floating point numbers, but this is sort of the premise of how it works and how we want the model to look at different tokens and how they relate to one another. So that's what the attention mechanism looks like under the hood. So this is what the actual GPT or decoder only transformer architecture looks like. And yeah, so I'm just going to go through this step by step here, and then we can hopefully jump into some of the math and code behind how this works. So we have our inputs, embeddings, and positional encodings. We have only decoder blocks, and then some linear transformation, and then pretty much just we do some softmax probability distribution. We sample from those, and then we start just generating some output, and then we compare those to our inputs and see how off they were, optimize from that. In each of these decoder blocks, we have our multi-head attention, res connections, feed-forward network, which consists of a linear, ReLU, linear, in that order, and then another res connection. In each of these multi-head attentions, we have multiple heads running in parallel, and each of these heads is going to take a key, query, and value. These are all learnable linear transformations, and we're going to basically dot product the key and query together, concatenate these results, and do a little transformation to sort of summarize it afterwards. And then what actually goes on in the dot product attention is just the dot product of the key and query, the scaling to prevent these values from exploding, to prevent the vanishing gradient problem, and then we have our masking to make sure that the model isn't looking ahead and cheating. And then softmax, matrix multiply, we output that, and then kind of fill in the blank there. So cool. This is a little bit, pretty much the transformer architecture, a little bit dumbed down, a little smaller in complexity to actually understand, but that's kind of the premise of what's going on here. So still implements a self-attention mechanism. So as you can see now, I am currently on my MacBook M2 chip. I'm not going to go into the specs of why it's important, but really quick, I'm just going to show you how I SSH onto my other PC. So I go SSH, just like that, and then I type in my IPv4 address, and then I just get a simple password from here, password that I've memorized. Cool. So now I'm on my desktop computer, and this is the command prompt that I use for it. So awesome. I'm going to go ahead and go into the free code camp little directory I have. So cd desktop, cd python testing, and then here I'm actually going to activate my CUDA virtual environment. Oop, not accelerate. I'm going to go CUDA activate. Cool. And then I'm going to go cd into free code camp GPT course. Awesome. So now, if I actually do code on here like this to open up my VS Code, it doesn't do that. So there's another little way I have to do this. And you have to go into VS Code, go into the little remote explorer here, and then you can simply connect. So I'm just going to connect to the in current window itself, there's an extension you need for this called OpenSSH server, I think is what it's called. And simply the same password I used in the command prompt, if I can type it correctly. Awesome. So now it's SSH'd into my computer upstairs. And I'm just going to open the little editor in here. Nice. So you can see that it looks just like that. That's wonderful. So now I'm going to open this in a Jupyter notebook. Actually, cd into desktop here, cd python testing, CUDA scripts, activate, cd free code camp GPT course, and then code, like that, and it will open. Perfect. How wonderful is that? And I've already done a little bit of this here, but we're gonna jump into exactly how we can build up this transformer or GPT architecture in the code itself. So I'm going to pop over to my Jupyter notebook in here. Cool. And now this little address, I'm going to paste that into my browser. Awesome. So we have this GPT v1 Jupyter notebook. So what I've actually done is I've done some importations here. So I've imported all of these Python importations, all the hyperparameters that we used from before. I've imported the data loader, I've imported the tokenizer, the train and val splits, the get batch function, estimate loss, just everything that we're going to need. And it's all in neatly organized little code blocks. So awesome. Now what? Well, let's go ahead and continue here with the actual upgrading from the very top level. So I remember I actually showed, and you can skip back to this, I actually showed the architecture of the GPT sort of lined out in, I guess, a little sketch that I did. And all we're going to do is pretty much build up from the high level, the high level general architecture down to the technical stuff, down to the very root dot product attention that we're going to be doing here. So I'm going to go ahead and start off with this GPT language model, which I just renamed. I replaced Bigram with GPT here. So that's all we're doing, and I'm going to add some little code bits and just walk through step by step what we're doing. So let's do that. So great. Next we're going to talk about these positional encodings. So I go back to the paper here, or rather this architecture. We initially have our tokenized inputs, and then we give them embeddings, so token embeddings, and then a positional encoding. So this positional encoding, going back to the attention paper, is right here. So all it does is every even token index, we apply this function, and then every odd token index, we apply this function. You don't really need to know what it's doing, other than the fact that these are the different sine and cosine functions that it uses to apply positional encodings to the tokenized inputs. So on our first index or whatever, let's say we have hello world, okay? There's 5 characters here. H will be at index 0, so it'll get an even encoding function, and then E will be odd since it's index 1, so it'll get this one, and then L will get this, the next L will get this, and then, or I don't know if I messed up that order, but essentially it just iterates and it goes back and forth between those, applying these fixed functions. And the thing is with fixed functions is that they don't actually learn about the data at all because they're fixed. So another way we could do this would be using nn.embedding, which is what we use for the token embedding. So I'm going to go ahead and implement this here in our GPT v1 script. So I'm going to go ahead and add on this line self.position embedding table, nn.embedding block size. So the block size is the length or the sequence length, which in our case is going to be 8. So there's going to be 8 tokens,
and this means we're going to have 8 different indices, and each one is going to be of size n.embed. And this is a new parameter I actually want to add here. So n.embed will not only be used in positional embedding, but it will also be used in our token embedding, because when we actually store information about the tokens, we want that to be in a very large vector. So not necessarily a probability distribution, or what we were using before in the bigram language model, but rather a really large vector, or a list, you could think about it, as a bunch of different attributes that are about a character. So maybe, you know, A and E would be pretty close because they're both vowels, versus like E and Z would be very different because Z is not a very common letter and E is the most common letter in the alphabet. So we pretty much just want to have vectors to differentiate these tokens, to place some semantic meaning on them. And anyways, that's a little talk about what token embedding table is going to do when we add n.embed. And then positional embedding table is just the same thing, but instead of each character having its own thing, each letter index in the input is going to have its own embedding. So I can go and add this up here, the n_embed, and we can just make this maybe 384. So 384 is quite huge. This may be a little too big for your PC, but we'll see in a second. So what this is going to do is it's going to have a giant vector. It's going to be like, I don't know, we could say like embedding, embedding vector, and then it would be like this, and you would have a bunch of different attributes, so like 0.1, 0.2, 0.8, 1.1, right? Except instead of 4, this is 384 elements long. And each of these is just going to store a tiny little attribute about that token. So let's say we maybe had like a 2-dimensional, and we were using a word. So if we had sad versus happy, sad might be 0.1, and then 0.8, or 0.8, whereas happy, sad would be maybe the positivity of what it's saying, and then 0.8 would be is it showing some sort of emotion, which is a lot, right? It's 80% emotion, and then 0.1 of maybe positive sentiment. And then if we had 0.9 would be happy, because it's happy, it's very good. And then 0.8 is emotional, because they're sort of the same on the emotional level. But yeah, so this is what our embedding vectors are pretty much describing, and all this hyperparameter is concerned with is how long that vector actually is. So anyways, let's continue with the GPT language model class. So the next bit I'd like to talk about is how many decoder layers we have. So in here, let's just say we have 4 decoder layers, all right? So we have 4 of these. It's going to go through this one, and then this one, and then this one, and then this one. This is all happening sequentially. So we could actually make a little sequential neural network with 4 decoder layers. So I'm actually going to add this in, and then a little bit of extra code, which I'll explain in a second here. So this self.blocks is how many decoder blocks we have running sequentially, or layers. Blocks and layers can be used interchangeably in this context. But yeah, we have an n.sequential, and this asterisk is pretty much saying we're going to repeat this right here for how many n layer is. And n layer is another hyperparameter we're going to add. We go n_layer, we go equals 4, okay? So n_layer equals 4. That means it's going to make 4 of these, I guess, blocks or layers sequentially. It's going to make 4 of them. And this little block thing, we're going to build on top of this in a second here. We're going to make an actual block class, and I'm going to explain what that does. But for now, this is going to be some temporary code. As long as you understand that this is what, this is how we create our 4 layers, our 4 decoder layers. That's all you need to know for now. I'm going to move more into this block later. As for this self dot layer norm final, this is the final layer norm. All this is going to do is we're just simply going to add this to the end of our network here. Just simply at the end here, and all this is going to do is just going to help the model converge better. Layer norms are super useful, and yeah, so you'll see more how that works. I'll actually remove it later on, and we'll actually compare and see how good it actually does. And you can totally go out of your way to experiment with different normalizations and see how well the layer norm helps the model perform, or how well the loss sort of converges over time when you put the layer norm in different places. So let's go back here, and now we have this end here, which is the language. I believe this is language modeling head or something. Again, this is what Andrei Karpov used. I'm assuming that means language modeling head. But pretty much all we're doing is we're just projecting, or we're doing this final transformation here, this final little linear layer here from all of these sequential decoder outputs, and we're just going to transform that to something that the softmax can work with. So we have our layer norm afterwards to sort of normalize, help the model converge after all this computation. We're going to feed that into a linear layer to make it, I guess, softmax workable, so the softmax can work with it. And yeah, so we're just simply projecting it from an embed, which is the vector length that we get from our decoder, and this vocab size. So the vocab size is going to essentially give up a little probability distribution on each token that we have, or the vocabulary. So anyways, I'm going to make this back to normal here, and we're going to just apply this to the forward pass. So a little thing I wanted to add on to this positional embedding, or rather just the idea of embeddings versus the fixed definite function of that, the sinusoidal functions and the cosine functions that we used here. These are both actually used in practice. The reason I said we're going to use embeddings is because we just want it to be more oriented around our data. However, in practice, sinusoidal encodings are used in base transform models, whereas learned embeddings, what we're using, are used in variants like GPT. And we are building a GPT, so we're probably going to find better performance from learnable embeddings. And this is just something that the experts do. It's just a little practice that experts do when they're building transformer models versus variants like GPTs. So that's just a little background on why we're using learnable embeddings. So now let's continue with the forward pass here. So I'm going to paste in some MAR code, and let me just make sure this is formatted properly. Cool. So we have this token embedding, which is our token embedding table. We take an IDX. We got our token embedding here. Then what we do with this positional embedding table is we have this torch.arrange. We make sure this is on the CUDA device, the GPU device, so it's in parallel. And all this is going to do is it's going to look at how long is t, and let's say t is our block size. So t is going to be 8. So all it's going to do is give us 8 indices. It's going to be like 0, 1, 2, 3, 4, 5, 6, 7. There's 8 of those, and we're essentially just going to give each of those indices a different n embedding vector for each of those indices. Just a little lookup table, and that's what that is. So all we do now is, it's actually quite simple, and this is a very efficient way to do it, is you just add these two together. So torch broadcasting rules, which you might want to look into. I'll actually search that up right now. Torch, also we'll search broadcasting semantics, PyTorch. Broadcasting, I cannot spell. Broadcasting semantics. So these are a little bit funky when you look at them the first time, but pretty much these are just rules about how you can do arithmetic operations and just operations in general to tensors. So tensors are like, you think of matrices where it's like a 2 by 2. Tensors can be the same thing, but they could be like a 2 by 2 by 2 or a 2 by 2 by 2 by 2 by 2 by 2 by 2, whatever dimension you want to have there. And pretty much it's just rules about how you can have two of those weirdly shaped tensors and do things to them. So just some rules here. I would advise you familiarize yourself with these, even play around with it if you want, just for a few minutes, and just get an idea for just try to multiply tensors together and see which ones throw errors and which ones don't. So it's a good idea to understand how broadcasting rules work. Obviously this term is a little fancy, and it's like, ooh, that's like a crazy advanced term. Not really, just it's pretty much just some rules about how you're multiplying these really weirdly shaped tensors. So yeah. Anyways, if we go back to here, we are allowed to broadcast these. We're allowed to actually add them together. So the positional embedding and the token embedding, we get X from this, which is a B by T by C shape. So now, what we can do with these is we can actually feed it in to the GPT, or I guess sort of a transformer network, if you want to say that. So we have these embeddings and positional encodings. We add these together, and then we feed them into our sequential network. So how are we doing this? Well, we go self.blocks, which is up here, and we essentially just feed an X, which is literally exactly what happens here. We have our tokenized inputs, we got our embeddings and our positional encodings through learnable embeddings, we add them together, and then we feed them into the network directly. So that's all that's happening here, and that's how we're feeding an X, which is the output of these. Then after all of this is like way after we've gotten through all of these GPT layers or blocks, we do this final layer norm and then this linear transformation to get it to a softmax, to get it to essentially probabilities that we can feed into our softmax function. And then other than that, this forward pass is exactly the same other than this little block of code here. So if this makes sense so far, that is absolutely amazing. Let's continue. I'm actually going to add a little bit of, in practice, some little weight initializations that we should be using in our language model and in module subclass. So I'm going to go over a little bit of math here, but this is just really important for practice and to make sure that your model does not fail in the training process. This is very important. It's going to be a little funky on the conceptualizing, but yeah, bring out some pen and paper and do some math with me. We've built up some of this initial GPT language model architecture, and before we continue building more of it and the other functions, some of the math stuff that's going on and the parallelization that's going on in the script, I want to show you some of the math that we're going to use to initialize the weights of the model to help it train and converge better. So there's this new thing that I want to introduce called standard deviation. And this is used in intermediate level mathematics. The symbol essentially looks like this: population standard deviation. So n, the size, so it's just going to be an array, the length of the array, and then xi, we iterate over each value, so x at position 0, x at position 1, x at position 2, and then this u here is the mean. So essentially, we're going to iterate over each element. We're going to subtract it by the mean. We're going to square that and then keep adding all these squared results together. And then once we get the sum of that, we're going to we're going to divide this by the number of elements there are. And then once we get this result, we're going to square root that. So this symbol here might also look a little bit unfamiliar. And let me just illustrate this out for you. So we go to our whiteboard, and this E looks like that. Let's just say we were to put in x, I, like that. And our array, let's just say for instance, our array is 0.1, 0.2, 0.3. So what would the result of this be? Well, if we look at each element, iteratively add them together, so 0.1 plus 0.2 plus 0.3, well, we get 0.6 from that. So this would essentially be equal to 0.6. That's what that equals. We just add each of these up together, or we do whatever this is iteratively. Whatever this element is, we iterate over the number of elements we have in some arbitrary array or vector or list or whatever you want to call it. And then we just sort of look at what's going on here, and we can do some basic arithmetic stuff. So let's walk through a few examples just to illustrate to you what the results look like based on the inputs here. So I'm going to go back to my whiteboard. We're going to draw a little line here just to separate this, and let's go down. So I want to calculate the standard deviation, do standard deviation of, and then we'll just make some random array, negative 0.38, oh, negative 0.38, 0.52, and then 2.48. Cool. So we have this array. This is 3 elements. So that means n is going to be equal to 3. Let me drag this over here. So n is the number of elements. So n is going to be equal to 3. Our mean, well, our mean is just, we add all these up together and then we average them. So our mean is going to be equal to, let's just say negative 0.38 plus 0.52 plus 2.48, and then divided by 3. And the answer to this, I did the math ahead of time, is literally 0.873 repeated, but we're just going to put 0.87 for simplicity's sake. Cool. So the mean of this is 0.87 and n is equal to 3. Now we can start doing some of the other math. So we have this O, has a cool line, and we do square root 1 over n, which is equal to 3, and then we multiply this by sigma. That's what this symbol is. That's sigma. That's the name for it. And then we go x I minus, and then our mean of 0.87. Apologies for this sloppy writing. And then we square that. So cool, let me drag this out. Awesome. So let's just do this step by step here. So the first one is going to be 0.38. So we have negative 0.38. And we're going to do minus the mean here. So minus 0.87. And I'm just going to wrap all this in brackets so that we don't miss anything. I'm going to wrap it in brackets and then just square it and see what we get after. So I'm just going to write all these out, then we can do the calculations. So next up we have 0.52 minus 0.87. We'll square that. And then next up we have 2.48 minus 0.87. And then we square that as well. So awesome. What is the result of this? The result of negative 0.38 minus 0.87 squared is 1.57. The result of this line is 0.12. These are all approximations. They're not super spot on. We're just doing this to understand what's going on here. Just to overview the function, not for precision. Then the next one is going to be 2.59. And you can double check all these calculations if you'd like. I have done these preemptively, so that is that. And now from here, all we have to do is add each of these together. So 1.57 plus 0.12 plus 2.59 divided by 3 is 1.57 plus 0.12 plus 2.59. All of that divided by 3 is going to be equal to 1.42. And then keep in mind we also have to square root this. So the square root of that is going to be 1.19 approximately. We'll just add this guy ahead of it, a little approximation thing. And so that's what the standard deviation of this array is. Negative 0.38, 0.52, 2.48. The standard deviation is approximately 1.19. Awesome. Let's do another example. So let's say we want to do the standard deviation of 0.48, 0.5, 50, I guess, 0.52. Cool. So there's a little pattern here. It just goes up by 0.02 each time. And you're going to see why this is vastly different than the other example. So let's walk through this. So first of all, we have n. N is equal to 3. Cool. What is our mean? Our mean, well, if you do our mean is 0.5. If you do 0.48 plus this plus that, and divided by 3, that's going to be 0.5. And if you're good with numbers, you'll probably already be able to do this in your head, but that's okay if not. Next up, we're going to do this in the formula. So, what do these iterations look like? So, let's just do these in brackets like the old way, minus 0.5 squared. The next one is 0.5 minus 0.5 squared, which we already know is 0. And then this one is 0.52 minus 0.5 squared. So the result of 0.48 minus 0.5 squared, and we'll just write equals here, is going to be approximately 0.02 squared. So that would be 0.004, like that. So I'll make this not actually overlap. 0.004. And then this one we obviously know would be 0, because 0.5 minus 0.5, that's 0. And then you square 0, still the same thing. And then this one is 0.0004 as well. So when we add these two together, we're going to get 0.0008, just like that. And then if we divide them by 3 or whatever n is, then we end up getting 0.00026 repeating. So I'll just write 266 like that. And so all we have to do at this point is just find the square root of this, and we'll just do square root of 0.0026 approximately, and that's going to be equal to about 0.0163. So that is our standard deviation of both of these arrays here. So 0.048 and then 0.5 and then 0.52. Our standard deviation is 0.0163, so very small. And then we have negative 0.38, 0.52, and 2.48. We get a standard deviation of 1.19. So you can see that these numbers are vastly different. One is literally 100 times greater than the other. So the reason for this is because these numbers are super diverse. They, I guess another way you could think of them is that they stretch out very far from the mean. So this essentially means when you're initializing your parameters, that if you have some outliers, then your network is gonna be funky, because the learning process is just messed up because you have outliers and it's not just learning the right way it's supposed to. Whereas if you had way too small of a standard deviation from your initial parameters, like in here, but maybe even smaller, so let's say they were all 0.5, right? Then all of your neurons would effectively be the same and they would all learn the same pattern. So then you would have no learning done. So one would either be your learning is super, super unstable and you have outliers that are just learning very distinct things and not really letting other neurons get opportunities to learn, or rather other parameters to learn. If you have a lot of diversity, you just have outliers, and then if you have no diversity at all, then essentially nothing is learned and your network is useless. So all we want to do is make sure that our standard deviation is balanced and stable so that the training process can learn effective things. So each neuron can learn a little bit. So you can see here, this would probably be an okay standard deviation if these were some parameters, because they're a little bit different than each other. They're not all like super, super close to the same. And yeah, so essentially what this looks like in code here is the following. So you don't actually need to memorize what this does, as it's just used in practice by professionals. But essentially what this does is it initializes our weights around certain standard deviations. So here we set it to 0.02, which is pretty much the same as what we had in here. So this one's a little bit off than the standard deviation we set here, but essentially we're just making sure that our weights are initialized properly. And you don't have to memorize this at all. It's just used in practice, and it's going to help our training converge better. So as long as you understand that we can apply some initializations on our weights, that's all that really matters. So cool. Let's move on to the next part of our GPT architecture. So awesome. We finished this GPT language model class. Everything's pretty much done here. We did our init, we did some weight initializations, and we did our forward pass. So awesome. That's all done. Now let's move on to the next, which is the block class. So what is block? Well, if we go back to this diagram, each of these decoder blocks is a block. So we're pretty much just going to fill in this gap here. Our GPT language model has these two, where we get our tokenized inputs, and then we do some transformations and a softmax after. And essentially we're just filling in this gap here, and then we're going to build out and just sort of branch out until it's completely built. So let's go ahead and build these blocks here. What does this look like? That's what this does. So we have our init, we have a forward pass as per usual, init, and a forward pass as seen in the GPT language model class, though all of them are going to look like this, forward and an init. So the init is going to just initialize some things. It's going to initialize some transformations and some things that we're going to do in the forward pass. That's all it's doing. So what do we do first? Well, we have this new head size parameter introduced. So head size is the number of features that each head will be capturing in our multi-head attention. So all the heads in parallel, how many features are each of them capturing? So we do that by dividing n embed by n head. So n head is the number of heads we have, and n embed is the number of features we have, or we're capturing. So 384 features divided by 4 heads. So each head is going to be capturing 96 features, hence head size. So next up we have self.sa, which is just short for self-attention. We do a multi-head attention. We pass in our n head and our head size, and you'll see how these parameters fit in later once we build out this multi-head attention class. So cool. Now we have a feed forward, which is as explained just in the diagram here. Our feed forward is just this, which we're actually going to build out next. And we have 2 layer norms, and these are just for the post-norm / pre-norm architecture that we could implement here. In this case, it's going to be post-norm, just because I found that it converges better for this course and the data that we're using and just the model parameters and whatnot. It just works better. So also that is the original architecture that we use in the attention paper. So you might have seen that they do an add and norm rather than a norm and add. So anyways, we've initialized all of these. Cool. So we have head size, self-attention, feed forward, and then 2 layer norms. So in our forward pass, we do our self-attention first. Let's actually go back to here. So we do our self-attention, then add a norm, then a feed forward, and then add a norm again. So what does this look like? Self-attention, add a norm, feed forward, add a norm. Cool. So we're doing an add. So we're going X plus the previous answer, which is adding them together, and then we're just applying a layer norm to this. So cool. If you want to look up more into what layer norm does and everything and why it's so useful, you can totally go out of your way to do that, but layer norm is essentially just going to help smoothen out our features here. So we have this, and honestly there's not much else to that. We just return this final value here, and that's pretty much the output of our blocks. So next up, I'm going to add a new little code block here, which is going to be our feed forward. So let's go ahead and do that. So feed forward, just going to look exactly like this. It's actually quite simple. So all we do is we make an nn.sequential, torch.nn. We make this sequential network of linear, ReLU, and then linear. So in our linear, we have to pay attention to the shapes here. So we have nembed, and then nembed times 4, and then the ReLU will just essentially, what the ReLU will do is it looks like this. Let me illustrate this for you guys. So essentially, you have this graph here, and let's just make this a whole plane actually. So all of these values that are below 0, all these values that are below 0 on the x-axis and equal to 0 will be changed just to 0 like that. So you have all these values that look like this, and then everything that is above 0 just stays the same. So you essentially just have this funny looking shape. It's like straight and then diagonal. That's what the ReLU function does. It looks at a number, sees if it's equal to or less than 0. If that's true, we give that number 0, and if it's not, then we just leave the number alone. So cool. Very cool nonlinearity function. You can read papers on that if you'd like, but essentially the shape of this just doesn't matter. All we're doing is we're just making sure that we're just converting some values if they're equal to or below 0. That's all this is doing. And then we essentially are multiplying this, we're doing this linear transformation times this one. So we have to make sure that these inner dimensions line up. So 4 times nembed and 4 times nembed, those are equal to each other. So our output shape should be nembed by nembed. Cool. So now we have our dropout, and in case you don't know what dropout is, it pretty much just makes a certain percentage of our neurons just drop out and become 0. This is used to prevent overfitting and some other little details that I'm sure you could figure out through experimenting. So all this actually looks like in a parameter form is just dropout equals, we'll just say 0.2 for the sake. So 0.2 means 20%, or 0.2 is going to, so 0.2 in percentage form is just going to drop out 20% of our neurons, turn them to 0 to prevent overfitting. That's what that's doing. So cool. We have our feed forward network, we drop out after to prevent overfitting, and then we just call a forward on this sequential network. So cool. Feed forward, pretty self-explanatory. Let's jump into the next piece. We're going to add the multi-head attention class. So we've built all these decoder blocks. We've built, inside of the decoder blocks, we built the feed forward and our res connections. And now all we have to do left in this block is the multi-head attention. So it's going to look exactly like this here. We're going to ignore the keys and queries for now and save this for dot product attention. So we're going to, essentially just make a bunch of these multiple heads, and we're going to concatenate results and do a linear transformation. So what does this look like in code? Well, let's go ahead and add this here. All that attention, cool. So multiple heads of attention in parallel. I explained this earlier, so not going to jump into too much detail on that. But we have our init, we have our forward, and what are we doing in here? So our self.heads is just a module list, and module list is kind of funky. I'll dive into it a little bit later, but essentially what we're doing is we're having a bunch of these heads essentially in parallel for each head. So num heads, let's say our num heads is set to maybe 4 in this block. We do multi-head attention, we do n heads and then head size. So n heads and then head size, so num heads essentially what it is. So for the number of heads that we have, which is 4, we're going to pretty much make one head running in parallel. So 4 heads running in parallel is what this does here. Then we have this projection, which is essentially just going to project the head size times the number of heads to an embed. And you might ask, well, that's weird because num heads times this is literally equal to an embedding if you go back to the math we did here. And the purpose of this is just to be super hackable so that if you actually do want to change these around, it won't be throwing you dimensionality errors. So that's what we're doing. It's just a little projection from our whatever these values are up to this constant feature length of an embed. So then we just follow that with a dropout, dropping out 20% of the network's neurons. Now let's go into this forward here. So forward. Torch.concatenate or torch.cat. We do for h in self.heads. So we're going to concatenate each head together along the last dimension. And the last dimension in this case is we do b batch by time by, we just say feature dimension or channel dimension. The channel dimension here is the last one. So we're going to concatenate along this feature dimension. And let me just help you illustrate what exactly this looks like. So when we concatenate along these, we have this b by t, and then we'll just say our features are going to be h1, like our each of our heads here, another h1, h1, h1. And these are all just features of head 1. And then our next would be h2, 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 h2. And then if, let's just say we have a third head, go h3, 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 like that. So we have maybe 4 features per head, and there's 3 heads. So essentially, all we're doing when we do this concatenate is we're just concatenating these along the last dimension. So to convert this like ugly list format of just each head features sequentially in order, which is like really hard to process, we're just concatenating these so they're easier to process. So that's what that does. And then we just follow this with a dropout. So we do our self.projection and then just follow that with a dropout. So cool. If that didn't totally make sense, you can totally just plug this code into ChatGPT and get a detailed explanation on how it works if something wasn't particularly clear. But essentially that's the premise. You have your batch by time or batch by sequence length or time used interchangeably. And then you have your features, which are all just in this weird list format of each feature just listed after another. So cool. That's what multi-head attention looks like. Let's go ahead and implement dot product attention or scaled dot product attention. So a little something I'd like to cover before we go into our next scaled dot product attention was just this linear transformation here. And you might think, well, what's the point if we're just transforming an embed to an embed, right? That it's just kind of weird to have them match like that. And essentially what this does is it just adds in another learnable parameter for us. So it has a weight and a bias. If we set bias to false like that, then it wouldn't have a bias, but it does have a bias. So another just wx plus b, if you will, a weight times x plus a bias. So it just adds more learnable parameters to help our network learn more about this text. So cool. I'm going to go ahead and add in this last but not least scaled dot product attention or head class. So there's going to be a bunch of these heads, hence class head, running in parallel. And inside of here, we're going to do some scaled dot product attention. So there's a lot of code in here. Don't get too overwhelmed by this, but I'm going to walk through this step by step. So we have our init, we have our forward. Awesome. So what do we do in our architecture here? So we have a key, a query, and a value. The keys and the queries dot product together. They get scaled by 1 over the square root of length of a row in the keys or queries matrix. So we'll just say maybe keys, for example, the row of keys, the length of a row in keys. And then we just do our masking to make sure the network does not look ahead and cheat. And then we do a softmax and a matrix multiply to essentially add this value weight on top of it. So cool. We do this key, or keep in mind this initialization is not actually doing any calculations, but just rather initializing the linear transformations that we will do in the forward pass. So this self.key is just going to transform and embed to head size, bias false, and then, the rest of these are just the same. And embed to head size because each head will have 96 features rather than 384. So we kind of already went over that, but that's just what that's doing. Cool. That's just a linear transformation that's happening to convert from 384 to 96 features. Then we have this self.register buffer. Well, what does this do, you might ask? Register buffer is essentially just going to register this no look ahead masking in the model state. So instead of having to reinitialize this every single head for every single forward and backward pass, we're just going to add this to the model state. So it's going to save us a lot of computation that way on our training. So our training time is going to be reduced just because we're registering this. So it's just going to prevent some of that overhead computation of having to redo this over and over again. You could still do training without this. It would just take longer. So that's what that's doing. So now we have this dropout, of course, and then in our forward pass, let's break this down step by step here. So we have a B by T by C. So batch by time by channel is our shape. We just unpack those numbers, and then we have a key, which is we're just calling this linear transformation here on an input X. And then a query, which is also calling the same transformation, but a different learnable transformation on X as well. So what we get is this, instead of B by T by C, we get B by T by head size, hence this transformation from 384 to 96. So that's what that is, and that's how these turn out here. So now we can actually compute the attention scores. So what do we do? We'll just say weight. We'll just say weights is our attention weights, or I guess you could say that. We have our queries, dot product matrix multiply with the keys transposed. So what does this actually look like? And I want to help you guys sort of understand what transposing does here. So let's go back to here and draw out what this is going to look like. So essentially what transposing is going to do is it is just going to make sure, and let me draw this out first. So let's say you had, I don't know, maybe A, B, C, D, and you have A, B, C, and D. Cool. Let's draw some lines to separate these. Awesome. So essentially what this does is the transposing puts it into this form. So if we didn't have transpose, then this would be in a different order. It wouldn't be A, B, C, D in both from like top to bottom, left to right type of thing. It would be in a different order, which would essentially not allow us to multiply them the same way. So when we do A by A times B, it's like sort of a direct multiply, if you will. I don't know if you remember times tables at all from elementary school, but that's pretty much what it is. We're just setting up in a times table form, and we're computing attention scores that way. So that's what that is. That's what this transposing is doing. And all this does is it just flips the second last dimension with the last dimension. So in our case, our second last is t and our last is head size, so it just swaps these two. So we get b by t by head size and then b by head size by t. We dot product these together, also keeping in mind our scaling here, which is taking this, we're just taking this scaling of 1 over the square root of length of a row in the keys. If we look at this here, now there's a little analogy I'd like to provide for this scaling right here. So imagine you're in a room with a group of people and you're trying to understand the overall conversation. If everyone is talking at once, it might be challenging to keep track of what's being said. It would be more manageable if you could focus on one person at a time, right? So that's similar to how a multi-head attention in a transformer works. So each of these heads divides the original problem of understanding the entire conversation, i.e. the entire input sequence, into smaller, more manageable subproblems. Each of these subproblems is a head. So the head size is the number of these subproblems. Now consider what happens when each person talks louder or quieter. If someone speaks too loudly, or the values in the vectors are very large, it might drown out the others. This could make it difficult to understand the conversation because you're only hearing one voice or most of one voice. To prevent this, we want to control how loud or how quiet each person is talking so we can hear everyone evenly. The dot product of the query and key vectors in the attention mechanism is like how loud each voice is. If the vectors are very large or high dimensional, or many people are talking, the dot product can be very large. To control this volume by scaling down the dot product using the square root of the head size. This scaling helps ensure that no single voice is too dominant, allowing us to hear all the voices evenly. This is why we don't scale by the number of heads or the number of time steps. They don't directly affect how loud each voice is. So in sum, multi-head attention allows us to focus on different parts of the conversation, and scaling helps us to hear all parts of the conversation evenly, allowing us to understand the overall conversation better. So hopefully that helps you understand exactly what this scaling is doing. So now let's go into the rest of this here. So we have this scaling applied for our head size, our head size dimension. We're doing this dot product matrix multiplication here. We get our b by t by t. And then what is this masked fill doing? So let me help you illustrate this here. So masked fill is essentially like, we'll say block size is 3 here, all right? So we have initially, let's say we have a like a 1, a 0.6, and then like a 0.4, okay? And then our next one is, we'll just say all of these are the same, okay? So essentially, in our first one, we want to mask out everything except for the first time step. And then when we advance one, so let's just change this here back to 0. When we go on to the next time step, we want to expose the next piece. So 0.6, I believe it was. And then a 0 again. And then when we expose the next time step after that, we want to expose all of them. So just kind of what this means is as the time step advances in this sort of, I guess, vertical part, is every time this steps 1, we just want to expose one more token or one more of these values sort of in like a staircase format. So essentially what this masked fill is doing is it's making this t by t, so block size by block size. And for each of these values, we're going to set them to negative infinity. So for each value that's 0, we're going to make that the float value negative infinity. So it's going to look like this. Negative infinity, negative infinity, negative infinity, just like that. So essentially what happens after this is our softmax is going to take these values and it's going to exponentiate normalize them. We already went over the softmax previously, but essentially what this is going to do, this last dimension here, concatenate, or not concatenate, rather apply the softmax along the last dimension, is it's going to do that in this sort of horizontal here. So this last t, it's like block size by block size. So it's like, we'll say t1 and t2, each of these being length of block size. We're just going to do it to this last t2 here, and this horizontal is t2. So hopefully that makes sense. And essentially what this exponentiation is going to do is it's going to turn these values to 0, and this one is obviously going to remain a 1, and then it's going to turn these into 0, and it's going to probably sharpen this 1 here. So this 1 is going to be more significant. It's going to grow more than the 0.6 because we're exponentiating. And then same here. So this 1 is going to be very, very sharp compared to 0.6 or 0.4. So that's what the softmax does. Essentially the point of the softmax function is to make the values stand out more. It's to make the model more confident in highlighting attention scores. So when you have one value that's like very big, but not too big, not exploding because of our scaling, right? I want to keep in mind our scaling. But when a value is big, when a score or attention score is very big, we want the model to put a lot of focus on that. And to say this is very important in the entire sentence or the entire thing of tokens, and we just want it to learn the most from that. So essentially that's what softmax is doing. Instead of just normalizing mechanism, it's just doing some exponentiation to that to make the model more confident in its predictions. So this will help us score better in the long run if we just highlight what tokens and what attention scores are more important in the sequence. And then after this softmax here, we just apply a simple dropout on this way variable, this new calculated way, scale dot product attention, masked, and then softmaxed. We apply a dropout on that. And then we perform our final weighted aggregation. So this V multiplied by the output of the softmax. Cool. So we get this V self.value of X, so we just multiply that. A little pointer I wanted to add to this module list, which is, module list here. And then where did it go? Yes, our sequential network here. So we have this sequential number of blocks here for n layers, and we have our module list. So what really is the difference here? Well, module list is not the same as n.sequential in terms of the asterisk usage that we see. In the language model class, module list doesn't run one layer or head after another, but rather each is isolated and gets its own unique perspective. Sequential processing is where one block depends on another to synchronously complete. So that means we're waiting on one to finish before we move on to the next, so they're not completing asynchronously or in parallel. So the multiple heads in a transformer model operate independently, and their computations can be processed in parallel. However, this parallelism isn't due to the module list that stores the heads. Instead, it's because of how the computation are structured to take advantage of the GPU's capabilities for simultaneous computation. And this is also how the deep learning framework PyTorch interfaces with the GPU. So this isn't particularly something we have to worry about too much, but you could supposedly think that these are sort of running in parallel. Yeah, so if you want to get into hardware, then that's like your whole realm there. But this is PyTorch. This is software, not hardware at all. I don't expect you have to have any hardware knowledge about GPUs, CPUs, anything like that. So anyways, that's just kind of a background on what's going on there. So cool. So let's actually go over what is going on from the ground up here. So we have this GPT language model. We get our token embeddings, positional embeddings. We have these sequential blocks, initialize our weights. For each of these blocks, we have this class block. So we get a head size parameter, which is n embedded of 384 divided by n heads, which is 4. So we get 96 from that. That's the number of features we're capturing. Self-attention, we do a feed forward 2 layer norms. So we go self-attention layer norm, feed forward layer norm in the post norm architecture. Then we do a feed forward, just a linear followed by a ReLU followed by a linear, and then dropping that out. And then we have our multi-head attention, which just sort of structured these attention heads running in parallel and then concatenates the results. And then for each of these heads, we have our keys, queries, and values. We register a model state to prevent overhead computation excessively. Then we just do our scaled dot product attention in this line. We do our masked fill to prevent look ahead. We do our softmax to make our values sharper and to make some of them stand out. And then we do a dropout finally on that and just some weighted aggregation. We do our weights, or this final weight variable multiplied by our weighted value from this initially, this linear transformation. So cool. That's what's happening step by step in this GPT architecture. Amazing. Give yourself a good pat on the back. Go grab some coffee, do whatever you need to do, even get some sleep, and get ready for the next section. This is going to be pretty fun. So there's actually another hyperparameter I forgot to add, which is nLayer. And nLayer is essentially, we'll just say equal to 4. nLayer is essentially equal to the number of decoder blocks we have. So instead of like n block, we just say n layers. It doesn't really matter what it's called, but that's what it means. And then number of heads is how many heads we have running, theoretically in parallel. And then n embed is the number of total dimensions we want to capture from all the heads concatenated together type of thing. We already went over that, so cool. Hyperparameters, block size, sequence length. Batch size is how many of these do we want at the same time. Max iters is just training, how many iterations we want to do. Learning rate is, well, we covered that in actually the Desmos calculator that I showed a little while back, just showing how we update the model weights based on the derivative of the loss function. And then val iters, which was just reporting the loss. And then lastly, the dropout, which is dropping out 0.2 or 20% of the total neurons. So awesome. That's pretty cool. Let's go ahead and jump into some data stuff. So I'm going to pull out a paper here called
So let's just make sure everything works here. Models. And then we're actually going to download our data. So I want to try to run some iterations and just make sure that actually I made some changes. Pretty much this was weird and didn't work. So I just changed this around to making our characters empty, opening this text file, opening it, storing it in a variable with UTF-8 format, and then just making our vocab this sorted list set of our text, and then just making the vocab size the length of that. So let's go ahead and actually run this through. And I did change the block size to 64, batch size 128, some other hyperparameters here. So honestly, the block size and batch size will depend on your computational resources. So just experiment with these. I'm just going to try these out first, just to show you guys what this looks like. Okay, so looks like we're getting IDX is not defined. Where could that be? Okay, yep. So this is, so we could just change that. It's just saying IDX is not defined. We're using index here, IDX there, so that should work now. And we're getting local variable t reference before assignment. Okay, so we have some, well, we have t here, and then we initialize t there. So let's just bring that up to there. Cool. Now let's try and run this. Oh, shape is invalid for input size of, okay, let's see what we got. So it turns out we don't actually need 2 token embedding tables. A little bit of a silly mistake, but we don't need 2 of those. So I'll just delete that. And then what I'm going to do is go ahead and run this again. We'll see a new error. Local variable t reference for assignment. Okay, so our t is referenced here. And well, how can we initialize this? What we can do is we could take this index here of shape b by t, because it goes b by t plus 1, etc., and it just keeps growing. So we could actually unpack that. So we could go b and t is going to be index.shape. Just unpack that. So cool. So now we're going to run this training loop, and it looks like it's working so far. So that's amazing. Super cool. Step 0, train loss 4.4. That's actually a pretty good training loss overall. So we'll come back after this is done. I've set it to train for 3,000 iterations, printing every 500 iterations. So we'll just see the loss 6 times over this entire training process, or we should. I don't know why it's going to 100 eval iters. Eval iters, okay. Estimate loss is, okay. So we don't actually need eval interval. I'm gonna get rid of that. We'll just make this, sure, why not 100? We'll keep that. And it's just gonna keep going here. So we'll see our loss over time is hopefully gonna get smaller. So I'll come back when that's done. As for the data, we're gonna be using the Open Web Text corpus. And let's just go down here. So this is a paper called Survey of Large Language Models. All right. So I'll just go back to Open Web Text, wherever that is up. Let's just find this. Okay. So Open Web Text. This is consisted of a bunch of Reddit links or just Reddit upvotes. So if you go on Reddit and you see a bunch of those posts that are highly upvoted or downvoted, they're pretty much those pieces of text are valuable and they contain things that we can train on. So pretty much web text is just a corpus of all these upvoted links, but it's not publicly available. So somebody created an open source version called Open Web Text, hence open, and it's pretty much just an open version of this. So we're going to download that. There's a bunch of other corpora here, like Common Crawl, which is really, really big. So like petabyte scale data volume. You have a bunch of books, so this is a good paper to read over. It's just called A Survey of Large Language Models. You can search this up and it'll come up. You could just download the PDF for it. So this is a really nice paper. Read over that if you'd like. But anyways, this is a download link for this Open Web Text corpus. So you just go to this link. I have it in the GitHub repo. And you just go to download. And it'll bring you to this drive. So you can go ahead and right click this and just hit download. It'll say 12 gigabytes exceeds maximum file size that it can scan. So it's like, this might have a virus. Don't worry, it doesn't have a virus. This was actually created by a researcher. So not really bad people are in charge of creating text corpora. So go ahead and download anyway. I've actually already downloaded this. So yeah, I'll come back when our training is actually done here. So I'm actually going to stop here at iteration 2000 because we're not actually getting that much amazing progress. And the reason for this is because of our hyperparameters. So batch size and block size, I mean, these are okay. What we might want to change up is our learning rate. So some combinations of learning rates that are really useful is like 3 to the negative 3. You go 3e to the negative 4. You go 1e to the negative 3, 1e, 1e to the negative 4. So these are all learning rates that I like to play around with. These are just sort of common ones. It's up to you if you want to use them or not. But what I might do actually is just downgrade to 3e to the negative 4, and we'll retest it. As well, I'm going to bump up the number of heads and the number of layers so that we can capture more complex relationships in the text, thus having it learn more. So I'm going to change each of these to 8. We'll go 8. I'm going to go, actually kernel will go restart. Now we'll just run this from the top. And we'll run that. Cool. So let's see what we actually start off with and what our loss looks like over time. Cool. So we got step 1, 4.5, about the same as last time. It's like 0.2 off or something. So it's pretty close. Let's see the next iteration here. That's wonderful. So before we were getting like 3.1-ish or something around that range, 3.15. Now we're getting 2.2. So you can see that as we change hyperparameters, we can actually see a significant change in our loss. So this is amazing. This is just to sort of prove how cool hyperparameters are and what they do for you. So given that, let's start changing around some data stuff. So this right here is the Wizard of Oz text. It's just a simple text file. The size isn't super large, so we can actually open it all into RAM at once. But if we were to use the open web text, we cannot actually read 45 gigabytes of UTF-8 text in RAM at once. Just can't do that unless you have like maybe 64 or 128 gigabytes of RAM. This is really just not feasible at all. So we're going to do some data pre-processing here, some data cleaning, and then just a way to simply load data into the GPT. So let's go ahead and do that. So the model has actually gotten really good at predicting the next token. As you can see, the train loss here is 1.01. So let's actually find what the prediction accuracy of that is. So I might just go into GPT-4 here and just ask it, what is the prediction accuracy of loss 1.01? The loss value comes with a loss function during the printing process. Okay, so let's see. Cross entropy loss doesn't mean the model is 99% accurate. Okay. So that pretty much means that the model is really accurate, but I want to find a value here. So if we'll go to Wolfram Alpha and we'll just guess some values here. So negative ln of, let's say, 0.9. Okay, so probably not that. 0.3, 0.2, 0.4, 0.35. Yep, so the model has about a 35% chance of guessing the next token as of right now. So that's actually pretty good. So 1 in every 3 tokens are spot on. So that is wonderful. This is converging even more. We're getting 0.89. So now it's getting like 40% are being guessed properly. Our validation is not doing amazing though, but we'll linger on that in a little bit here, and you'll see sort of how this changes as we scale our data. But yeah, So I've installed this webtext.tar file. Tar file is interesting. So in order to actually extract these, you simply just right click on them, you go extract to, and then it'll just make a new file here. So it'll process this. You have to make sure you have WinRAR or else this might not work to the fullest extent. And yeah, so we'll just wait for this to finish up here. You should end up with something that looks like this. So open web text, and inside of here you have a bunch of XZ files. Cool. So there's actually 20,000 of these. So we're gonna have to do a lot of, there's definitely gonna be some for loops in here for sure. So let's just handle this step by step in this data extract file. So first off, we're gonna need to import some Python modules. We're gonna use OS for interacting with the operating system, LZMA for handling XZ files, which are a type of compressed file, like 7-zip, for example, and then TQDM for displaying a progress bar. So you see a progress bar go left to right in the terminal, and that is pretty much going to show us how quick we are at executing the script. So next up, we're going to define a function called xzFilesIndir that takes a directory as an input, returns a list of all of the XZ file names in that directory. It's going to use os.listdir to get all the file names, and os path is file to check if each one is a file and not a directory or symbolic link. If a file name ends with .xz and it's a file, it'll be added to the list. So we just have a bunch of these files. Each element is just the title of each file in there. So that's pretty much what that does. And then next up here, we'll set up some variables. Folder path is just going to be where our XZ files are located. So I'm actually going to change this here because that's like an incorrect file path. But yes, just like that. You have to make sure that these slashes are actually forward slashes, or else you might get bytecode errors. So when it actually tries to read the string, it doesn't think that these are separated, or the backward slashes do like weird things to them. So you could either do like a 1 forward slash or 2 backward slashes, and that should work. So awesome. Just make sure you have forward slashes and you should be good. So folder path is where all these files are located. All these XZ files are located, as you saw. Output file is the pattern for output file names in case we want to have more than one of them. So if you want to have 200 output files instead of 1, then it'll just be like output 0, output 1, output 2, etc. And then a vocab file is where we want to save our vocabulary. Keep in mind, in this giant corpus, you can't push it onto RAM at once. So what we're going to do is, as we're reading these little compressed files, 20,000 of them, we're going to take all of the new characters from them and just push them into some vocab file containing all of the different characters that we have. So that way we can handle this later and just pretty much sort it into some list containing all of our vocabulary. Split files. How many files do we want to split this into? So pretty much this it ties back to output file and just these curly braces here. How many do we want to have? If we want to have more than one, then this would take effect. So cool. Now we'll use our xFilesIndir to get a list of file names and store them in this variable. We'll count the number of total XZ files, simply the length of our file names. Now in here, we'll calculate the number of files to process for each output file. If the user has requested more than one output file, this is the total number of files divided by the number of output files, rounded down. So if the user only wants one output file, max count is the same as total files, and that's how that works. So next up, we'll just create a set to store our vocabulary when we start appending these new characters into it. A set is a collection of unique items, in case you did not know entirely what a set was. Now, this is where it gets interesting. Now we're ready to process our .xz files. For each output file, we'll process max count files. For each file, we'll open it, read its contents, and write the contents to the current output file. and then add any unique characters to our vocabulary set. After processing max count files, remove them from our list of files. And then finally, we'll write all of our vocabulary to this file. So we pretty much just open, we just write all of these characters in the vocab to this vocab file, which is here, vocab.txt. So awesome. Now, honestly, we could just go ahead and run this. So let's go ahead and go in here. I'm going to go CLS to clear that. We'll go Python data extract.py. Let's see this work its magic. How many files would you like to split this into? We'll go 1. Then we get a progress bar, 20,000 files, and we'll just let that load. I'll come back to you in about 30 minutes to check up on this. Okay, so there's another little thing we want to consider for, and it's actually quite important, is our splits. So our train and val splits, it would be really inefficient to just get blocks and then creating, train and val splits as we go, every new batch we get. So in turn, what we might be better off doing is just creating an output train file and an output val file. So just 2 of them instead of 1. Train is 90% of our data, val is 10% of our data, if that makes sense. So pretty much what I did is I took away that little input line for how many files do you want. As you can see, I got quite a bit of files produced here by not doing that correctly. So don't do that. And yeah, essentially we're pretty much just doing that. So we're processing some training files. We're separating 90% of the names on the left side and then 10% of the names on the right side. We're just separating those into 2 different arrays, file names, and then we're just processing each of those arrays based on the file names. So I took away that little bit that was asking, how many files per split do you want? So I took that away, and this is like effectively the same code, just a little bit of tweaks. And yeah, so I'm going to go ahead and run this. Data extract. Cool. So we got an output train, and then after this, it's going to do the output validation set. So I'll come back after this is done. So awesome. I have just downloaded got both these splits, output train and val train. So just to confirm that they're actually the right size, got 38.9 and then 4.27. So if we do this divided by 9, so about 38.9 divided by 9, we get 4.32, and that's pretty close to 4.27. So we can confirm that these are pretty much the length that we expect them to be. So awesome. We have this vocab.txt file. Wonderful. So now what we have to focus on is getting this into our batches. So when we call our get batch function, actually cd out of this, open this in a Jupyter notebook. Just copy my desktop, paste it over here, and perfect. So go to this open web text folder with these files. Awesome. And our GPT v1. So this get batch function is going to have to change. Also, these are going to have to change as well. And this one too. These are probably not going to be here. But pretty much, let's go ahead and first of all, get this vocab.txt in. So what I'm going to do is I'm just going to go, we're going to go open web text / we'll go vocab.txt. Cool. So that's our vocab right there. Text read, vocab size, the length of that, nice. So that's what our vocab is. And then what we're going to do next is change this get batch function around. So first of all, I'm going to go ahead and get rid of this here, get rid of that data. And then I've actually produced some code specifically for this. So I'm just going to go back to my, I just need to find this folder. Okay. So I've actually produced some code here. I produced this off camera, but pretty much what this is going to do is it's going to let us call a split. Okay. So we have our get batch function. All of this down here is the same as our GPT v1 file. And then this data is just going to get a random chunk of text, so a giant block of text. And the way that we get it is actually pretty interesting. So the way that we get this text is something called memory mapping. So memory mapping is a way to look at disk files or to open them and look at pieces of them without opening the entire thing at once. So memory mapping. Look at, I'm not a hardware guy, so I can't really talk about that, but yeah, memory mapping is pretty cool and allows us to look at little chunks at a time in very large text files. So that's essentially what we're doing here. We pass in this split, file name is equal to train split. This is just an example text file. If the split is equal to train, then this is our file name, else file split. And then we're going to open this file name in binary mode. This has to be in binary mode. It's also a lot more efficient in binary mode. And then we're going to open this with a mem map. So I don't expect you to memorize all the mem map syntax. You can look at the docs if you would like, but I'm just going to explain sort of logically what's happening. So we're going to open this with the memory map library, and we're going to open this as mm. So the file size is literally just the length of it. So determining the file size. And all we're doing from this point is we're just finding a position. So we're using the random library, and we're finding a position between 0 and the file size minus block size times batch size. So pretty much we have this giant text file. We could either, what we want to do is we want to start from 0 and go up to like just before the end, because if we actually sample that last piece, then it's still going to have some wiggle room to reach further into the file. If we just made it from like the like the very start of the file to the very end, then what it would want to do is it would want to look past the end, because it would want to look at more tokens from that. And then we would just get errors because you can't read more than the file size, if that makes sense. So that's why I'm just making this little threshold here. And yeah, so that's what that does. That's the starting position. It could be a random number between the start and a little margin from the end here. So next up, we have this seek function. So seek is going to go to the start position, and then block is going to read. We're going to go up to the start position. So it's going to seek up to there. That's where it's going to start. It's going to go up to it. And then the read function is going to find a block of text that is block size times batch size. So it's going to find a little snippet of text in there at the starting position, and it's going to be of size. It's going to have the same amount of, I guess, bytes as block size times batch size, then all of that minus 1, just so that it fits into this start position. We don't get errors here. That's why I put the minus 1. But yeah, so we'll get a pretty decent text amount, I guess you could say. So it's going to be enough to work with. You could of course increase this if you wanted to. You could do like, times 8 if you wanted. Do like times 8 and then times 8 up here, but we're not going to do that. Based on my experience, this has performed pretty well. So we're going to stick with this method here. And then we just decode this bit of text. The reason we decode it is it's because we read it in binary form. So once we have this block of text, we actually have to decode this to UF8 format or UTF-8 format. And then any like bytecode errors we get, we're just going to ignore that. This is something you learn through practice, is when you start dealing with like really weird data, or if it has like corruptions in it, you'll get errors. So all you want to do is, all this does is it pretty much says, okay, we're just going to ignore this bit of text and we're just going to sample everything around it and not include that part. And plus, since we're doing so many iterations, it won't actually interfere that much. So we should be all right. And then for this replace little function here, I was noticing I got errors about this /r. So all this does is it just replaces that with an empty string. And then finally, we have all this decoded data. So all we're going to do is just encode this into the tokenized form. So it's all in It's all in the tokenized form, integers or torch.longs data type. And we just, that's what our data is. Instead of a bunch of characters, it's just a bunch of numbers. And then we return that into our get batch. And this is what our data is. So that's pretty cool. We can get either train or val split. And that's sort of what it looks like in practice. That's how we sample from very large text files at a smaller scale, bit by bit. So let's go ahead and implement this here. I'm gonna go grab this entire thing and pop over to here. I'm just going to replace that. So get random chunk, get batch. Cool. So now we can actually go ahead and perhaps run this. Actually, before we run this, there's a little something we need to add in here. So I have this train split.txt and a val split.txt. So I actually need to change these. So we'll just go rename, we'll go train split.txt and then val split.txt. Cool. And then we could just go open web text / and then same thing for here. Cool. Let's go ahead and run this now. Oh, and we're getting errors. Memmap is not defined. Okay. So that's another thing we need to probably add in then. So I'm actually just going to stop this process from running here. We're going to go pip install memmap. Oh, memmap is not defined. Oh, we don't actually need to install this. It by default comes with the operating system. So what we actually need to do is we just close this. GPT v1. Awesome. Is everything? Everything is good. Nothing is broken. Sweet. So what I actually need to do up here is import this. So I need to go import memmap, just like that. And should be good to start running the script. Name random is not defined. Again, another importation we have to make. Import random. And we should start seeing some progress going here. So once we see the first iteration, I'm going to stop it, come back at the last iteration, and then we'll start adding some little bits and pieces onto our script here to make it better. So we're already about 600 iterations in, and you can see how the training loss has actually done really well so far. So it's gone from 10.5, dropped all the way to 2.38, and we can actually see that we might be able to actually get a val loss that is lower than the train. Because keep in mind, in train mode, the dropout takes effect, but in val, in eval mode, let me just scroll up to this here. Yes, so model.eval, what this does is it turns off the dropout. So we don't lose any of the neurons, and they're all sort of showing the same features and giving all the information that they're supposed to because they're all active. But in train mode, 20% of them are off. So once you actually see in eval mode it does better, that means that the network has started to form a sense of completeness in its learning. So it's just adjusting things a little bit once it hits that point, and we might see this happen momentarily. But this is really good progress so far. A loss of 1.8 is amazing. So yeah, in the meantime, I'm just going to add some little tweaks here and there to improve this script. So I've actually stopped the iteration process, but we've gotten to 700 steps, and we can already see that val loss is becoming less than train loss, which is showing that the model is actually converging and doing very well. So this architecture is amazing. We've pretty much covered every architectural, math, PyTorch part that this script has to offer. The only thing I want to add, or actually a few things I want to add, one of them being torch.load and torch.save. So one thing that's going to be really important when you start to scale up your iterations is you don't just want to run a script that executes, a training loop with an architecture and that's it. You want to have some way to store those learnable parameters. So that's what torch.load and torch.save does. So I have some file right? And you can pretty much, you could put it into like a serialized format. When you save it, you take your initial architecture. In our case, it would actually be the GPT language model. So you would save this because it contains everything, all these other classes as well. They're all inside of GPT language model. You would save that architecture and you'd essentially serialize it into some pickled file that would have the file extension .pkl. So essentially, instead of using Torch, we're just going to use a library called Pickle because they're essentially the same thing. Pickle's a little bit easier to use, or at least a little bit easier to understand. There's less to it. Pickle will only work on one GPU. So if you have like 8 GPUs at the same time, you're going to want to learn a little bit more about hardware stuff and some PyTorch docs. But pretty much, if we want to save this after training, what we're going to do is we're going to use a little library called Pickle, and this comes pre-installed with Windows. On my type of Windows, import Pickle. Okay. So what we want to do is implement this after the training loop, after all these parameters have been updated and learned to the fullest extent. So after this training loop, we're simply going to open. We're going to do with open, and we could just go model 001 like that. And then just that a .pkl is the file extension for it. And then since we're writing to it, we're going to go write binary as f. And then in order to actually save this, we just go pickle.dump. And then we can use model and then just f like that. So if I start recording this, it's going to make, if I start recording this training process, it's going to make my, it's going to make my clip lag. So I'm going to come back to this after we've done, let's just say about 100 iterations. We're going to do 100 iters, and I'm going to come back and show you guys what the model file looks like. What I actually did is I changed some of the model hyperparameters because it was taking way too long to perform what we wanted it to. So I changed and head to 1 and layer to 1, and I half batch size all the way down from 64 to 32. So what I'm actually going to add here is just to make sure, I like to print this out at the beginning, just print device, make sure that the device is CUDA. Let's go back down. So it did in fact train the model. So we got all this done. And yeah, so I don't know why I did 2.54 or whatever that was just the entire loss. Okay. So model saved. Awesome. What does this actually look like here? So this model.pkl, 106 megabytes. Isn't that wonderful? So this is our model file. This is what they look like. It's just a serialized, pretty much the entire architecture, all the parameters of the model, the state, everything that it contains. And we just can compress that into a little PKL file, take that out, decompress it, and then just use it again with all those same parameters. So awesome. And all this really took was we just open as this, we do a pickle.dump, and then just to make sure that it actually saved, I just like to add a little print statement there. Cool. So next, what I'd like to add is a little way for us to, instead of just doing all of our training at once and then saving the model, being able to train multiple times. So I'm going to go up here, up to our GPT language model here. And let's just see what I'm going to do. I'm going to go with open, and we're going to go model 01 PKL, and we're going to go read binary. So we're actually going to read it. We're going to load this into our script here. So I'm going to go as f, and then I believe it's pickle.load. You just go, yeah, model equals pickle.load, and then we'll just essentially dump that right in there. Go print loading model parameters dot dot dot, and then just put f in there. And then once it is loaded, we'll do print loaded successfully. So I'm actually going to try this out now. Go do that. Boom, 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 and boom. Okay. So loading model parameters loaded successfully, and we'll actually see this start to work on its own now. So is it going to begin or is it not going to begin? Let's run that. Okay, perfect. So now we should take the loss that we had before, which was about 2.54, I believe, something along those lines. You can see that our training process is greatly accelerated. So we had 100. Now it's just going to do an estimate loss. Cool. And we're almost done. 1.96. Awesome. And the model's saved. So essentially what we can do with this is we can now save models, and then we can load them and then iterate further. So if you wanted to, you could create a super cool GPT language model script here, and you could essentially give it like 10,000 or 20,000 iterations to run overnight. You'd be able to save it and then import that into, say, a chatbot if you want. So that's pretty cool, and that's just kind of a good thing, good little. I mean, it's kind of essential for language modeling, because what's the point in having a machine learning model if you can't actually use it and deploy it? So you need to save for this stuff to work. All right, now let's move on to a little something in this task manager here, which I'd like to go over. So this shared GPU memory here and this dedicated GPU memory. So dedicated means how much VRAM, video RAM, does your GPU actually have on the card. So on the card, it's going to be very quick memory, because the electrons don't have to travel as quickly. That's kind of the logic of it. The electrons don't have to travel as far, because the little RAM chip is right there. So dedicated GPU memory is a lot faster. Shared GPU memory is essentially, if this gets overloaded, it'll use some of the RAM on your computer instead. So this will typically be about half of your computer's RAM. I have 32 gigabytes of RAM on my computer, so 16.0 makes sense. Half 32. And yeah, so you want to make sure you're only using dedicated GPU memory. Having your shared GPU memory go up is not usually a good thing. A little bit is fine, but dedicated GPU memory is the fastest, and you want everything to stick on there. Just try to make sure all of your parameters sort of fit around this, whatever your max capacity is. Maybe it's 4, maybe it's 8, maybe it's 48, who knows. And a good way to figure out what the highest amount of RAM you can use on your GPU without it getting memory errors or using shared memory is to actually play around with these parameters up here. So block size and batch size, actually let me switch those around. Those are not supposed to be in that order, but all good. Make our batch size 64, it's 128, okay. So batch size and block size are very big contributors to how much memory you're going to use. Learning rate is not, max iterations is not, evaluators is not, but these three will. So these are the amount of features that you store, the amount of heads you have running in parallel, and then also n layers. So some of these will not affect you as much because they're more sort of restrained to computation, how quickly you can do operations if something is sequential. So n layer won't strain you as much as something like batch and block size. But those are just good little things to sort of tweak and play around with. So I found the optimal sort of set of hyperparameters for my PC, and that happened to be 8, 384. Learning rate stays the same, and then 64, 128 for this. So that happened to be the optimal hyperparameters for my computer. It'll probably be different for yours if you don't have 8 gigabytes of RAM on your GPU. So anyways, that's a little something you have to pay attention to make sure you don't run out of errors. And a technique you can use, which I'm not actually going to show you in this course, but it's quite useful, is something called auto-tuning. And what auto-tuning does is it pretty much runs a bunch of these, a bunch of models with different sets of hyperparameters. So it'll run like batch size 64, batch size 32, batch size 16, batch size maybe 256. It'll be like, okay, which ones are throwing errors and which ones aren't. So what it'll do, if you properly set up an auto-tuning script, is you will be able to find the most optimal set of parameters for your computer, most optimal set of hyperparameters that is possible. So auto-tuning is cool. You could definitely look more into that. There's tons of research on it. And yeah, so auto-tuning is cool. Let's dig into the next part. The next little cool trick we use in practice, especially by machine learning engineers, is a little something called arguments. So you pass an argument into, not necessarily a function, but into the command line. So this is what it'll look like. This is just a basic example of what arg parsing will look like. So just go Python arg parsing, because that's the script's name. I go dash LLMs, because that's what it says right here. This is what the argument is. And then we can just pass in a string, say hello. The provided whatever is hello. So cool. You can add little arguments to this, and I'm even going to change this around. Let's say batch size, and then we'll just go like that. Batch size, please provide a batch size. I can do the same thing again. And see, it says following arguments required are batch size. So that obviously didn't work. And if we actually try it the correct way, argparsing.py, then we go dash batch size. We can make it 32. Oop. Oh, that's because it's not a string. So what we need to actually do is, it's BS somewhere. Okay. So args, parse args. So we need to change this to BS like that. And we can go batch size. Batch size is 32. Okay. So even I'm a little bit new to arguments as well, but this is something that comes in very handy when you're trying to, each time you're trying to change some parameters. If you add, new GPU or whatever, and you're like, oh, I want to double my batch size. It's like, sure, you can easily do that. So a lot of the times it won't just have one, but you'll have like many, meaning like maybe a dozen or so of these little arguments. So that is what this looks like. And we're going to go ahead and implement this into our little script here. So I'm just going to pop over to GPT-1. I'm going to pull this up on my second monitor here. And in terms of, these, I'm just going to start off by making a importation arg parser, or arg parse rather, that's what it's called. And then we go parser is equal to, I'll just copy and paste this entire thing in, why not? Cool. Okay. So we get like batch size or something. And then we'll add in the second part here. So args, parse the arguments here. And then we'll just go batch size like that. Our batch size is equal to whatever that was. And we'll just go args.batch size. So cool. I'm gonna run this, and not defined. Yes, so I got a little not defined thing here, and pretty much all I missed was that we return this. So essentially, this should be equal to this right here. So I'm just going to go ahead and copy that, and boom, parse args, except we don't have a parse args function. So what do we need to do instead? Well, actually that might just work on its own. Let's try it out. Okay, so it looks like it's actually expecting some input here in code. So that's probably working. And if we ported this into a script, then it would simply ask us for some input. So I believe we're doing this correctly. Let's go ahead and actually switch over and port all of this into some code. So I'm going to make a training file and a chat file. So the training file is going to be all of our parameters, whatever, all of our architecture, and then the actual training loop itself. We're going to have some arguments in there. And then the chatbot is going to be pretty much just a question answer thing that just reproduces text. So it'll just be like prompt completion type of thing. And yeah, so let's go ahead and implement that here. So in our GPT course here, I'm going to go training.py, and we're going to go chatbot.py, just like that. So in training, let's go ahead and drag everything in here. I'm just going to move this over to the second screen and just copy and paste everything in order here. So next up we have our characters, and then we have our tokenizer, and then our get random chunk and get batches. Sweet. Our estimate loss function. And then this giant piece of code containing most of the architecture we built up. I'm just going to add that in there. Cool, we're not getting any warnings. And then the training loop. And the optimizer. Awesome. And then after this, we would simply have this context, but the point of this is that we want to have this in our chatbot script. So what I'm going to do is in this training.py, I'm going to keep all of these the same. I'm going to keep this entire thing the same, get rid of this little block of code, and we're going to go into the chatbot here. So loading model parameters, good. We want to load some in, train some more, and then dump it. Chatbot is not going to dump anything. It's just going to save. So I'm going to take all of our training here. And instead of dumping, take that away. We'll also take away the training loop as well. Okay. I don't believe we have anything else to actually bring in. We don't need our get batch. We do not need our get random chunks. So awesome. We're just importing these parameters by default like that. Awesome. So from this point, we have imported our model. Cool. So let's go ahead and port in our little chatbot here, this little end piece, which is going to allow us to essentially chat with the model. So this is what it looks like. A little while loop. We have a prompt where we just input something. Prompt next line. That should be fairly self-explanatory. Then we have this tensor. We're going to encode this prompt into a bunch of integers or torch.long data types on the GPU, where device is CUDA. And then after we've actually generated these, so model.generate, we're going to unsqueeze these. Remember, it's a torch.tensor, so it's going to be in the matricey form. So it's going to look like this. It's going to look like this or whatever. That's essentially what the shape is. So all we're doing when we unsqueeze it is we're just taking away this wrapping around it. So awesome. And then we're just doing max2 tokens, for example, 150 here, and then to a list format, and then we can just print these out as generated characters. Awesome. So it's just going to ask us prompt and then do some compute, give us a completion, so on and so forth. So that's what this is doing here. And another thing I wanted to point out is actually when we load these parameters in, at least on training, it's going to initially give us errors. If we don't have a model to load it from, we're going to get errors from that because the model will just not be anything and we won't be able to import stuff. So that's going to give you errors first of all. Another thing you want to pay attention to is to make sure that when you've actually trained this initial model, that it matches all of the architectural stuff and the hyperparameters that you used, that when you're using to load up again. So when you're running your forward pass and whatnot, you just want to make sure that this architecture sort of lines up with it, just so that you don't get any architectural errors. Those can be really confusing to debug. So yeah, and the way we can do this is actually just commenting it out here. So awesome. We're able to save, load models, and we're able to use a little loop to create a sort of chatbot that's not really helpful because we haven't trained it an insane amount on data that actually is useful. So another little detail that's very important is to actually make sure that you have NN module in all of these classes and subclasses. NN.module basically works as a tracker for all of your parameters. It makes sure that all of your NN extensions run correctly, and just overall a cornerstone for PyTorch, like you need it. So make sure you have NN module in all of these classes. I know that block sort of comes out of GPT language model and so on and so forth, but just all of these classes with NN or any learnable parameters, you will need it in. It's overall just a good practice to have NN module in all of your classes overall, just to sort of avoid those errors. So cool. I didn't explicitly go over that at the beginning, but that's just a heads up. You always want to make sure NN module is inside of these. So cool. Now, something I'd like to highlight is a little error that we get when we try to generate when we have max new tokens above block size. So let me show you that right now. So you just go Python chatbot and then batch size 32. So we could say hello, for example. Okay, so it's going to give us some errors here. And what exactly does this error mean? Well, when we try to generate 150 new tokens, what it's doing is it's taking the previous, HELLO exclamation mark 6 tokens, and it's pretty much adding up 150 on top of that. So we have 156 tokens that we're now trying to fit inside a block size, which in our case is 128. So of course, 156 does not fit into 128, and that's why we get some errors here. So all we have to do is make sure that what we could do is make sure that max new tokens is small enough, and then be sort of paying attention when we make prompts, or we could actually make a little cropping tool here. So what this will do is it'll pretty much crop to the last block size tokens. And this is super useful because it pretty much doesn't make us have to pay attention to max new tokens all the time, and it just essentially crops it around that 128 limit. So I'm going to go ahead and replace index here with index cond or index condition, and we go ahead and run this again. So I could say hello, and we get a successful completion. Awesome. We can keep asking new prompts. I can just type. And awesome. So yeah, we're not really getting any of these dimensionality, like architecture fitting type errors, if you want to call them, if you want to make it super fancy that way. But yeah, there's not really that much else to do. Yeah, there's a few points I want to go over, including fine tuning. So I'm going to go over a little illustrative example as to what fine tuning actually looks like in practice. So in pre-training, which is what this course is based off of, in pre-training, you have this giant text corpus, right? You have this giant corpus here with some text in it. And essentially what you do is you take out little snippets. These are called blocks or batches or chunks, you could say. You take out little batches of these, you sample random little blocks, and you take multiple batches of them. And you essentially have this, let's just say HELLO, and maybe the next maybe the outputs or the targets rather are ELLO exclamation mark. So it's just shifted over by 1, and so given this sequence of characters, you want to predict this, which is just the input shifted by 1. That's what pre-training is. And keep in mind that these are the same size. This is 1, 2, 3, 4, and 5. Same thing here. These are both 5 characters long. Fine-tuning, however, is not completely the same. So I could have hello, and then maybe like a question mark, and it would respond, the model might respond, how are you? Maybe that's just a response that it gives us. We can obviously see that hello does not have the same amount of characters or the same amount of indices as how are you. So this is essentially the difference between fine-tuning and pre-training. With fine-tuning, you just have to add a little bit of different things in your generate function to compensate for not having the same amount of indices in your inputs and targets, and rather just generate until you receive an end token. So what they don't explicitly say here is at the end of this question, there's actually a little end token, which we usually do. It usually looks like this. So we go like that, or like this. These are end tokens, and then you typically have the same for start tokens, so like an S or start, like that. Pretty simple. And essentially you would just append them. End and a start token. The start token doesn't matter as much because we essentially just are looking at what this does, and then we start generating. The start doesn't really matter because we don't really need to know when to start generating. It just happens. But the end token is important because we don't want to just generate an infinite number of tokens, right? Because these aren't the same size. It could theoretically generate a really, really long completion. So all we want to make sure is that it's not generating an infinite amount of tokens, consuming an infinite amount of computation, and just to prevent that loop. So that's why we append this end token to the end here. So you have this little end bit. And essentially, once this end token is sampled, you would end the generation. Simple as that. And we don't actually sample from the token itself, but rather the actual, I guess you could say, index, or the numerical value, the encoded version of end, which is usually just going to be the length of your vocab size plus 1. So if your vocab size in our case is like maybe 32,000, your end token would be at index 32,001. So that way, when you sample an end token, when you sample that 32,001 token, you actually just end the sequence. And of course, when you train your model, you're always appending this end token to the end. So you get your initial inputs, and then inside of either your training data, or when you actually are processing it and feeding it into that transformer, you have some sort of function that's just appending that little 32,001 token index to it. So that's pretty much what fine-tuning is. That sums up fine-tuning. And the whole process of creating these giant language models is to, of course, help people. And there's no better way to do that than to literally have all the information that humans have ever known, meaning like Common Crawl, Open Web Text, or Wikipedia, and even research papers. Pre-training on all of that. So just doing, again, same size, and then shift over for targets. And then after you've iterated on that many, many times, you switch over to fine-tuning, where you have these specifically picked out prompt and completion pairs, and you just train on those for a really long time until you are satisfied with your result. And yeah, that's what language modeling is. There are a few key pointers I want to leave you with before you head on your way to research and development in machine learning. So first things first, there's a little something called efficiency testing, or just finding out how quickly certain operations take. So we'll just call this efficiency testing, and I'll show you exactly how to do this right here. Efficiency. Yeah, I don't know if I spelled that correctly. I don't know why it's doing that. Okay. Anyways, we'll just pop into code here, and essentially we'll just do I don't know, time testing. Go import time, and essentially all we're going to do is we're just going to time how long operations take. So in here you can go, I don't know, you can go start time equals time.time, and essentially what this function does is it just takes a look at the current time right now, the current like millisecond, very, very precise, and we can do some little operation like, I don't know, for I in range. We'll just go, I don't know, 10,000. Go print I, for example, or print I times 2. Okay, and then we could just end the time here. So we'll go end time equals time.time again, calling the current time. So we're doing right now versus back then, and that little difference is how long it took to execute. So all we can do is we could say total time if you want. We could say total time equals end time minus start time, and we'll just go print end time, or time taken. Let's go total time like that. And we just execute this Python time testing. Cool. Time taken 1.32 seconds. So you can essentially time every single operation you do with this method, and you can see even in your, I encourage you to actually try this out. I'm not going to, but I encourage you to try out how long the model actually takes to do certain things. Like how long does it take to load a model? How long does it take to save a model? How long does it take to estimate the loss, right? Play around with hyperparameters, see how long things take, and maybe you'll figure out something new, who knows? But this is a little something we use to pretty much test how long something takes, how efficient it is, and then to also see if it's worth investigating a new way of approaching something in case it takes a ridiculous amount of time. So that's time testing and efficiency testing for you. The next little bit I want to cover is the history. I'm not going to go over the entire history of AI and LLMs, but essentially we originated with something called RNNs, okay? RNNs are called recurrent neural networks, and they're really inefficient, at least for scaled AI systems. So RNNs are essentially think of it as a little loop, keeps learning and learning, and this is sequential, right? It does this, and then this, and then this, and then this. It has to wait for each completion. It's synchronous. You can't have multiple of them at once because they're complex. GPUs cannot run complex things. They're only designed for just matrix multiplication and very simple math like that. So RNNs are essentially a little bit dumber than transformers, and they are run on the CPU. So RNNs was where we last sort of stopped at. And what I encourage you to do is look into more of the language modeling and AI history and research that has led up to this point, so you can have an idea as to how researchers have been able to quickly innovate given all these historical innovations. So you have like all these things leading up to the transformer. Well, how did they all philosophize up to that point? And yeah, it's just something good to sort of be confident in, is innovating as both a researcher, an engineer, and a business person. So cool. RNNs were where we sort of finished off, and now it's transformers and GPTs. That's the current state of AI. Next up, I would like to go over something called quantization. So quantization is essentially a way to reduce the memory usage by your parameters. So there's actually a paper here called Q-LoRa efficient fine-tuning of quantized LLMs. So all this does in simple form is it pretty much, instead of using 32-bit floating point numbers, it goes not only to 16-bit of half precision, but all the way down to 4. So what this actually looks like is in binary code or in byte code, it will look somewhere here. There's some array of numbers that it uses. Okay, I can't find it, but pretty much what it is it is a bunch of floating point numbers, and they're all between -1 and 1, and there are 16 of them. If you have a 4-bit number, that means it can hold 16 different values, 0 through 15, which is 16 values. And all you pretty much do is you have this array of floating point numbers. You use the bytecode of that 4-bit number to look up the index in that array, and that is your weight. That is the weight they use in your model. So this way, instead of using 32-bit and just having these super long numbers that are like super precise, you can have super precise numbers that are just generally good parameters to have that just perform decently. They're just sort of well spread out and experimented on, and they happen to work. And you have 16 of them instead of, a lot. So that's another cool little thing that's going on right now is 4-bit quantizations. It's a little bit harder to implement. I would encourage you to experiment with half precision, meaning 16-bit floating point numbers. So that means it occupies 16 on and off switches or capacitors on your GPU. And yeah, so quantization is cool to sort of scale down the memory, so that way you can scale up all of your hyperparameters and have a more complex model with these. Just essentially to have bigger models with less space taken up. So that is quantization. And this is the paper for it. This is a little link you can search up if you want to get more familiar with this and see sort of performance standards and whatnot. The next thing I'd like to cover is gradient accumulation. So you might have heard of this, you might not have heard of this. Gradient accumulation what gradient accumulation does is it will accumulate gradients over, say, we just set a variable x. So every x iterations, it'll just accumulate those iterations, average them. And what this allows you to do is instead of updating each iteration, you're updating every x iterations. So that allows you to fit more parameters and more info and more generalization into this one piece. So that way, when you update your parameters, it's able to generalize more over maybe a higher batch size or a higher block size. So when you distribute this over many iterations and average them, you can fit more into each iteration because it's sort of calculating all of them combined. So yeah, that's a cool little trick you can use if your GPU maybe isn't as big, if it doesn't have as much VRAM on it. So gradient accumulation is wonderful and it's used lots in practice. The final thing I'd like to leave you guys off with is something called Hugging Face. And you've probably heard a lot about this so far, but let me just guide you through and show you how absolutely explosive Hugging Face is for machine learning. So you have a bunch of models, data sets, spaces, docs, etc. And let's just go to models, for example. So just to showcase how cool this is, we have multimodal AIs, which could be like image and text or video, etc. Right? You have multiple different modes, so it's not just text or not just video, it's many different ones at the same time. So you have multimodal models, you have computer vision, you have natural language processing, and we're actually doing natural language processing in this course. We have audio, tabular and reinforcement learning. So this is really cool, and you can actually just download these models and host them on your own computer. So that is really cool. You also have data sets, which are even cooler. And these are pretty much just really high quality data sets of prompt and answer completions, at least for our purpose, if you want to use those. So you have question answering or conversational. So if I go to the Open Orca dataset, for example, it has 9,000 downloads, 500 likes. It has a bunch of IDs, system prompts, so you're an AI assistant, whatever. And then you have the cool stuff, which is you'll be given a definition of a task first and some input of the task, etc. And then the response. It's like, oh, we just gave it an input and asked it to answer in a format, and it actually did that correctly. So you could pretty much train these on a bunch of prompts that you would be able to feed into GPT-4 and try to make your model perform that way. And this actually has 4.23 million rows in the training split, which is amazing. So datasets are wonderful, and you can find the best ones, or at least the best fine-tuning datasets on OpenOrca. Really good. As for pre-training, I believe I mentioned this earlier in this survey of large language models paper that we put it down through Reddit links. Yep, so you could use like open web text, you could use Common Crawl, you could use books, you could use Wikipedia. These are all pre-training data sources. So yeah, hopefully that leaves you with a better understanding on how to create GPTs, transformers, and pretty good large language models from scratch with your own data that you scraped or that you downloaded. And yeah, that's it. Thanks for watching. So you've learned a ton in this course about language modeling, how to use data, how to create architectures from scratch, maybe even how to look at research papers. So if you really enjoyed this content, I would encourage you to maybe subscribe and like on my YouTube channel, which is in the description. I make many videos about AI, programming, and computer science in general. So you could totally feel free to subscribe there. If you don't want to subscribe, that's fine. You could always unsubscribe later if you want to. It's completely free. But yeah, I also have a GitHub repo in the description for all of the code that we used, not the data because it's way too big, but all of the code and the Wizard of Oz text file. So that is all in the GitHub repo in the description. Thanks for watching.